Hey everybody, hope you're doing well today. I want to look at our last bit of exponentials here before we move on to logarithms. Recently, we looked at compound interest, right? We ended up with a formula, okay, that we know will give us the amount in account of some principal invested at a certain interest rate, compounded a certain number of times a year. And we know that formula is that, right? The principal times 1 plus r over n to the nt. Okay. Here's the situation that I am going to, I want us to consider today. What if we invested $1? We got 100% annual interest for 1 year, compounded at the following frequencies. Okay, and you can see that I want to say, okay, what if it's compounded just annually? So once a year, semi-annually, monthly, weekly, daily, even down to the every minute. So let's work through this. If I take $1, it's my initial investment, and we are getting, let's see here, 100% annual interest, so that's just 1, okay, 1.0, right? Divided by, and it's compounded annually, we're just dividing that by once a year, to the once a year times how many years? 1 year. How much money do we have? Well, really, that's 1 times 2 to the first. So it's $2, right? That makes sense, right? We got 100% interest for 1 year. We started with $1. We now have $2 because we got $1 in interest. All right, semi-annually. We're starting with $1. We're taking 1 plus 100% interest. Semi-annually is twice a year. Okay, so we're dividing that by 2 to the twice a year times 1 year. And how much do we have there? Well, that would be 1 times 1.5 squared. 1.5 squared is 2.25. So we'd have $2.25. So, man, we made an extra quarter, okay, getting that interest semi-annually. Let's go to monthly. $1 times 1 plus 100% interest divided by 12 to the 12 times 1. Okay, so that's 1 and a 12th to the 12th power. I'm going to use my calculator. Okay, and I get $2.61. Wow, really raking it in now. But we shouldn't be surprised, right? Our account is getting bigger the more often it's compounded because we're getting interest on interest more frequently. All right, let's go to weekly. You guys okay if I stop writing that one out front? Because that's not really doing anything. So this would be 1 plus 1 over, there are 52 weeks in a year, so we're going to get that divided by 52 to the 52 times in 1 year. I'm going to stop writing that times 1 for the 1 year also. How much do we have with that? Okay, on my calculator, I have $2.69. Continuing to go up. Daily. 1 plus 1 over, that's 365 times a year. 365 times that we're getting that interest. Let's see what we have there. $2.71. Man, look at this go, right? Okay. How about every minute? 1 plus 1 over. All right, every minute. How many minutes in a year? 60 minutes in an hour. 24 hours in a day, 365 days in a year. If we multiply that out, we get 525,600. 525,600 minutes. That's right. I think I knew that. Okay. To the 525,600. Okay. What are we going to get this time? And when I put that in, I get $2.72. Actually, if I go back and I do some more decimals, if I go back to that daily, it's 2.7146, and this is actually 2.7183. So it got bigger, didn't it? But did it get a lot bigger? No. So my question for you is, how often are we going to have to compound it in a year to get to $3? I mean, would every second get us up to $3? Would every tenth of a second get us up to $3? Would we even get to $3? Could we get to $2.75? Or is there a horizontal asymptote that we're approaching? If I took this concept and I thought about it as a function and I used x instead of n, what would that function be? 1 times 1 plus 1 over, we'll call that x, to the, well, it's always to the same number, isn't it? To the x. That's the function. Let's graph that function in Desmos. There it is. Okay. And do you spot a horizontal asymptote? Where is it? Is it at y equals 3? No, not y equals 3. That's too high, isn't it? It's crossing over there. Is it at y equals 2.75? Well, that looks close. Hey, not quite 2.75, though. It's at y equals e. E is a special number. Okay? It's an irrational number. It's a number that shows up in mathematics so often, an irrational number that shows up in mathematics so often that it gets its special name. Okay? And mathematicians have decided to call it E. I shouldn't say mathematicians. I believe Euler, which is spelled E-U-L-E-R, that mathematician, is who the number E is named after. It's about, look at this right here, it's about 2.718. It's about that, isn't it? We almost got there. Now, it's irrational, so it goes on forever, doesn't repeat, so on. But that is this special base. And where did that number come from? It came from taking this function 1 plus 1 over x to the x and looking at what happens to that function as x goes to infinity. Now, this is some calculus notation that you probably haven't seen before. It's called a limit. Okay? The limit is what y value does the function approach as x goes to infinity, and that is that number e. Now, in our minds, okay, e we should think of as about 2.718. It's the base of an exponential that's about 2.718. Bigger than 2, smaller than 3. But it's called the natural base because it shows up in all kinds of places in mathematics where maybe we might not even expect it. Notice I titled this section 6.2, the natural base. E is the natural base. So, if it's a base, we should look at it as the base of an exponential function. So let's call this function f of x, and we're going to say it's e to the kx. Let me head back in Desmos. F of x equals e, well, let's just do e to the x first. That's what e to the x looks like. And if you think about it, it makes sense that it's exponential growth because our base e is 2.718. And let's just do a quick recall, okay, on exponential functions. Okay. When do we have exponential growth? Okay. We have growth, okay, when our base is bigger than 1, don't we? We have decay when our base is between 0 and 1. And this is for, b to the x, right? So the base of our exponential function, if it's more than 1, it's growth. And what does e to the kx, or e to the x look like? 2.718 to the x. It's exponential growth. There's 0, 1. If I go up to 1, it should be about 2.718. It should be e. There it is. Now let me throw this value of k in front, and I'm going to add a slider. Right now k is 1, so this is just e to the x. As I make k bigger, e to the 2x. What do we notice about the function? E to the 3x. As we make k bigger, it grows faster. Why does that make sense? Let's think about e to the 2x for a second. This is our function, e to the 2x. Well, if I think about properties of exponents, this is the same as e squared to the x, because power to a power we multiply, don't we? Okay. And what's e squared? E squared is 2.718 squared. If I go to my calculator, by the way, on the left side there's an e to the x button. It's right behind ln. So I'm going to take, there we go, e squared. E squared is about 7.39 to the x, right? So it makes sense it's growing faster because really our base is growing faster. So as k gets bigger, it grows faster. That makes sense. Now what happens as we cross from k equals 1 to k being less than 1? It's growing slower, okay? I think that makes sense. How about as we cross when k is 0? When k is 0, we've now switched to exponential decay. Let me look at that right there for a second. Two ways that we can think about why e to the negative x is exponential decay. First way you might think about it is, what does that negative do to the graph? If this is e to the x, when we put that x and we make it negative, what does it do to a graph? It's a reflection over the y-axis. There's e to the negative x. So you might say that makes sense that it's exponential decay because we're reflecting e to the x over the y-axis. Another way you might think about it might be similar to what I did over here. E to the negative x is really e to the negative first to the x. Power to power we multiply. Now e to the negative first is 1 over e. Now remember that e is about 2.718. So isn't 1 over 2.718 a number smaller than 1? Remember how I reminded us just a little bit ago that decay is when the base of the function is between 0 and 1. All right, so getting back to this. E to the kx is exponential growth when k is positive. It's exponential decay when k is negative. Now we have to keep that straight from just good old-fashioned b to the x, because b to the x is growth when b is greater than 1 and decay when the base is between 0 and 1. But for e to the x, it's when k, which is up in the exponent, is positive that makes it growth, and k being negative is what makes it exponential decay. I won't be having you graph natural base functions by hand because the points aren't nice. Other than, excuse me, the point 0, 1, every other y value is going to be an irrational number. All right? Okay? But what I am going to ask you to do is to make predictions on what the graph is going to look like, okay, off the equation, and then just use your graphing calculator to do it. So for example, f of x equals 3e to the 0.25x. Okay? That's 3e to the 1/4 x. Is that going to be growth or decay? Well, what did we just talk about? If k is positive and 1/4 is positive, the coefficient of the x is positive, it's going to be growth. So this is going to be exponential growth. What's the y-intercept going to be? 3. So I know it's going to be an exponential growth function whose y-intercept is 3. Let's graph that. There it is. Looks good. What did I predict e to the negative 0.75 x minus 2 plus 1 is going to look like? Well, first off, growth or decay. What's our value of k? Notice it's right here. It's negative. That tells me this is going to be a decay function. Now my y-intercept would be 1, but what things are we doing to the graph? So it's going to be an exponential decay function, but because of that minus 2, we know it's going to go left 2. That didn't work out like I wanted it to. Okay. It's going to go left 2 and it's going to go up 1. That means we have a horizontal asymptote now at 1, and our exponential decay function has slid over. There's e to the negative 0.75x. That's the exponential decay. But now when we subtract 2 from the x, you guys know, did I say left 2? Oh boy. I'm not going to pause the video. I think I said left 2. It should be right 2, shouldn't it? Oops. Where am I? Now we've moved it right 2, and plus 1. We've moved up the horizontal asymptote up 1. Hopefully you caught that if I didn't accidentally say left. It should go right. All right, last one. 1/2 e to the negative x plus 2. Notice our k is negative 1. This is going to be a decay function. The 1/2 out front, okay, we know it's going to vertically compress by 1/2. Plus 2 is going to move it up 2. Okay, so we're going to have a horizontal asymptote up 2. It's going to be vertically shrunk. Okay, squished down, should look something like that. There's e to the negative x. There's the 1/2 out front. And there's the plus 2 up 2. So on your practice, what I want you to do is I want you to make predictions. I want you to think about what the graph is going to look like, and then go ahead and graph it on a calculator, either one of these or on Desmos. So compound interest is really what started this conversation, right? Back here, remember this formula? We have a situation here where we are compounding our interest continuously. Remember how we were going faster and faster and faster, monthly, weekly, daily, every minute. And as our number of times we compounded a year got bigger and bigger and bigger, okay, more frequent, more frequent, more frequent, okay, that's what gave us the number e. Compounded continuously, okay, is a situation that can be modeled by this function. Our principal times e to the r times t. Now, interesting thing about this is notice our rate went from being in the base of our compound interest formula, if it's compounded a discrete number of times a year, to being up in the exponent. How did that rate slide from the base to the exponent? That's a really good question, and I would like you guys, if you want to take some time to see if you can figure that out on why that happens. So let's look at a situation here, okay, where you invest $4,000 in an account that pays 6% annual interest compounded continuously. How much interest have you earned in 10 years? So our new formula for compounded continuously is PE to the RT. So okay, we are going to take our initial investment of $4,000 times E. Our rate is 6%, and we are going for 10 years. So we'll grab our calculator, let's put that in. I have $7,288.48. Okay. How much interest have I earned? Well, if I subtract off the $4,000, I have earned $3,288.48. All right, so new formula. Now, I want to finish this off by asking the question, what account are you going to find that you're going to get interest that's compounded continuously? How often is continuously, by the way? If it's every second, it would be like this often is when you're getting kickbacks on your interest. If it's like half a second, it's like this. Okay? Continuously, you can't even tell the difference. Okay? It's just always happening. Where are we going to find an account that's going to do that? And the answer to that is nowhere. So I'd like to start with a money example because that's what we're familiar with compound interest. But let's actually take this concept and let's apply it to a natural base, a natural situation where something would be compounded continuously. Okay? Let's talk about how much light filters down through a body of water, right? So picture a lake, picture an ocean. Okay? You're at the top of the water, right? You're on the water. 100% of the sunlight reaches the water. But then what happens over time? Okay? The deeper you get, the less light gets through, right? The deeper you get, the darker it gets. Okay? So here's a function that gives L, the percent of surface light, so L for light, that filters down through bodies of water. Okay? Okay? We're going to use the natural base here. This is going to be continuous. And why does that make sense? Okay? How often does the light lose? Okay? Does the water lose some of the light that it's receiving? Is it just like at every foot, all of a sudden, poof, there's a less light, and then we had to wait until the next foot, and poof, there's less light? Or is it something that's constantly being filtered out, continuously losing light? It's like if you go down that much more, you're going to have less light. If you go down like 1/10 of an inch, there's going to be less light. Is it going to be noticeable to our eyes? No. Okay? But we are continuously losing light. That's why we're using base E. Now, the K, our rate is going to be a rate of decay, depends on the murkiness of the water, right? Really clear waters, you can see long ways down because lots of white light is reaching. But if you are on a lake or an ocean that's a little bit more stained, a little more murky, maybe you're familiar with that. Usually when I'm fishing, one of the things I pay attention to, is this a really clear body of water or is it more of a stained kind of brown water? What kind of water am I fishing in, right? So K is going to depend on the murkiness of the water. So let's say divers are working in fairly clear water. The K value is about 0.02, okay? Negative 0.02. And why does it make sense that the K is negative? Because the deeper we go, the less light we have. This is decay. Let's graph this equation, okay, just to see what it looks like. Where is it? Well, we got to zoom out here, don't we? There we are. Okay. When x is 0, okay, we're 0, what is this, meters? We're 0 meters deep. We have 100% of the surface light, right? But as we go deeper and deeper and deeper, the less light is making it down. Notice, according to our model, we'll never get to total darkness where 0% of the light is present. But notice even at like 200 meters deep, we're only getting 1.8% of the light from the surface. That's going to be really, really dark. Okay. Let's answer some questions now. Estimate the percent of surface light available at a depth of 30 meters. That just means we're going to put 30 in for x right there. You can do it on your calculator. Since I have Desmos, I'll just do it right here. What is L of 30? We have about 54.9% of our surface light. Estimate how deep the divers can ascend before only 50% of the surface light is available? Well, at 30 meters, there's 54.9%. So I'd expect this answer to be deeper than 30 meters. Now, how would we figure this out? Well, we have to solve, hey, where is this equation equal to 50? We'd have to put 50 over here and solve it. Now, we don't quite have the tools to do that. That's going to require logarithms. That's why I put the word estimate there. So I'm just going to graph y equals 50, and I'm going to figure out where my curve crosses that 50% threshold, about 34.7 meters. If they're working on a sunken watercraft on the ocean bottom and the ocean right there is 100 meters deep, how much surface light is available? We're going to go back and we're going to put 100 in for x. Okay. About 13.5% of the light is available. All right, so hopefully you know where this number E came from, right? It came from looking at our compound interest formula and looking at increasing how often things are compounded. Okay? And as we do that, as the n went bigger and bigger and bigger, as n went to infinity, we got this number E. Okay? It's this natural base. It has lots of applications to it. It'll show up in numerous places. Okay? But we wanted to make sure that we get that covered and we have that understanding of our base E exponentials. All right, thanks for watching. We'll see you later.